Good afternoon, everyone. Thank you for the opportunity to speak to you. It's fantastic to see so many of you here today. I want to take the opportunity this afternoon to talk about one of my most favorite things of all, and that's customers. So I want to use the customers that I'm going to talk about as a backdrop to some of the really disruptive trends that we see in the manufacturing market, and use that as a mechanism to explain our strategy and to help you understand a little bit more about what we're doing with our products and technologies. Because we see some pretty disruptive trends in the markets that manufacturers are facing today that are going to influence the way that they design and manufacture, because it's our belief that you can no longer really separate design from manufacture. The example that you see on the screen behind me is an excellent example of this. It's from Under Armour. It's their new Architect Futurist shoe, and it's sold out within 14 minutes of being available on their e-store. And you can see that it demonstrates a complete convergence between design and manufacture. It's 3D printed, and as you can see, if you just embraced 3D printing to produce a typical standard solid sole shoe, you wouldn't really be gaining any advantage from that new manufacturing paradigm. So you have to think about a different way to design if you're going to leverage that new manufacturing technology. And there are new forms of design that help you embrace sophistication and complexity in the way that you define geometry. And so for that reason, we don't think you can any longer consider CAD and CAM as two discrete elements that you just simply glue together. They have to converge into something new. And that's what I want to talk to you about this afternoon, is this era of push-button manufacturing and what we call the future of making things. And it's not just the very large organizations like Under Armour. They are a fantastic example of what's possible with this type of technology, but it also lowers the barrier to entry for new, innovative, disruptive startup companies. And that creates competitive threat for the established incumbents. Take, for example, Modbot. Modbot are based in San Francisco, and they're revolutionizing the world of six-axis robotics. What you see is an early-stage prototype. We're about a group of 20 engineers working across 3 different geographic locations. We're able to bring this product to market in just 6 months. And they've been able to win high-value contract orders with the likes of Siemens. So Siemens obviously are a world leader in automation equipment, and here you have a small disruptive startup who's able to win business with that type of organization because they're able to build a completely configurable 6-axis robot, and they're able to deliver it to you for under $14,000, which revolutionizes forms of production. And so we see this as one of the key trends that are influencing the design and manufacturing market. So the first one is these new forms of production are drastically changing the way people design and manufacture, and you can no longer separate these two things from one another. If you employ these new forms of production technology, you have to think about different ways to embrace design. And as you do that, you create tremendous amounts of data and information. And if you can place that data and information at the center of your business, then you're able to leverage some of the new cloud technologies available to help automate elements of that process. Because it's not just about building a digital pipeline, it's about being able to automate that digital pipeline so that you can retarget human assets at where they're most valuable, when they're creative and when they're driving innovation within your organization. And that, we believe, will change the very nature of work itself in our industry. So let's start by talking about production. There are a lot of trends in production. You're starting to see new forms of additive manufacture, and you're seeing lower barriers to entry for robotics. We're also starting to see a convergence between the manufacturing industry and the construction industry. You can see an excellent example of robotics applied to construction right above me on this screen. Now that's changing and influencing the way people produce designs. So I want to use a small analogy from another industry in which Autodesk operates, which is the media and entertainment sector. Now I want to talk a little bit about what it means to create a design definition. What you can see on the left is Woody from Toy Story back in the 90s. And when Woody was developed, he was developed manually. So you had a lot of modelers and graphic artists and animation artists that work together to produce Woody. And you can see that he was built primarily from conventional modeling techniques. And then you get into the 2000s, and Sulley comes along in Munster's Inc. And you can see that Sulley has got some quite sophisticated fur. And it would be pretty difficult for a human being to sit there and manually model all that hair. In fact, it would be completely unrealistic. That hair needs to be procedurally generated by a computer algorithm based on the physical conditions that that model is placed in. And I'll assert that there's no difference between that and what we're seeing in manufacturing as we start to embrace these new forms of additive manufacturing technology. So think about sintering. In this case, this is a metal powder-based sintering that Toyota produced of a cylinder head. Parametrics are a fantastic tool for creating things like ports, valves, mounting planes. But what you can see in this design is that they've embraced complexity. The cost of complexity in printing is free. It costs nothing. In fact, to add material costs money, so the more air and intricacy that you can introduce, the better. And so the lattice on the interior of what would have been a casting serves to lightweight this product, but it does a lot more than that, because you can see that the lattice is variational. It's computationally generated using algorithms that integrate simulation tools, so that not only does it lightweight the product, it acts as a thermal dissipation heat sink, which means you can run the engine at a higher temperature, at a higher pressure, and gain better performance. But of course, when you introduce that level of sophistication, because the manufacturing process supports it, you can no longer manually model that. You couldn't have a human being sit there and model that lattice structure. It needs to be computationally, procedurally generated based on simulation results. So how do you put that into practice? Well, let's take another customer example, in this case, Airbus. So Airbus have a corporate goal that by 2050, they will reduce CO2 emissions by 50%. That's a pretty tall order. So they're starting to look at a fleet of the future, which is great, but you have to start with some practical execution. And so what they've done is they've taken a step back and they've looked at their in-service aircraft, and they've selected areas of those aircraft where they want to apply some of this generative, computationally generated topology definitions in their existing designs. This is a divider. It's a bulkhead that sits at the rear of the aircraft. It's where the cabin crew have their jump seats located. So it has to withstand rigorous FAA testing and authorization, up to 10 Gs. And so it gives them an excellent practical example to start to employ some of these next generation technologies in in-service fleet aircraft today. And what they're doing to do that is they're using Autodesk's Generative Design service, because there isn't just one right solution to this problem. There are many competing constraints and parameters, and there are many different alternative forms of manufacturing process that you could employ. And for every parameter, there are hundreds of variables. And so if there were just 10 parameters with 10 variables, there'd be 10 to the power of 10 potential solutions in the solution universe. In fact, what you see here would stretch for miles and miles in every direction. And as a human being, it would be pretty difficult to evaluate what the best solution is. What most of us would do as engineers is pick something. We would pick a group of variables that we wanted to focus on. And then being good engineers, we'd probably iterate a little bit in the local vicinity of that solution domain. The problem with that is that the real best answer might be 3 miles up in that direction, and we would never find it because we would never be empowered enough to be able to browse that solution domain. And that's where generative design can help. What it does is it uses the computational power of the cloud to parallel compute sample solutions from the entire solution universe, so that we can look at the long tail if we want. We can pivot between things like force and stress, force and displacement. We can change the manufacturing process. We can look at weight, because again, this isn't topology optimization where you're just optimizing for the lightest weight structure. In this instance, we're looking at a variety of different parameters, and there are multiple right solutions. It all depends on what market requirements we're trying to solve for. And so what it does is it doesn't replace the engineer, it empowers the engineer to browse the entire solution domain and to do what they do best, make trade-off decisions. Not sit there modeling up geometry, that's redundant work, it's repetitive work, and it's not something that as a professional engineer you're best placed to do. Now, generative design has a lot of practical applications. In this example, you can see the support structure. We've generated 9 different alternative proposals that the engineer can evaluate. But I'd ask you to imagine that this might not represent the support structure for that divider. If you turned it flat plane, what it might represent is the ideal optimum path of inventory through your shop floor. And so generative services can be applied to a variety of different domain problems across the whole of the design and manufacturing spectrum. And when you're doing that, you're creating a tremendous amount of data, both at the design stage as well as at the physical production stage. And if you can place that data at the center of your business, as we help you do with our Forge developer platform, you can start to use that information to create more and more automation process opportunities. In this example, we've been working with machineering to take IoT data live from a shop floor and use it as the information to drive a plant layout so that we can start to do virtual commissioning. When you build a new plant, and this is on behalf of a customer, it usually takes them about 2 weeks to commission the plant physically, which is 2 weeks of lost productivity. But by using this data at the center of the business and building an immersive experience, we've enabled the customer to actually virtually commission the plant 50% faster. That's a week of extra productivity from a manufacturing facility. We go to the next slide. You able to move the... Okay, so our assertion here is that by putting data at the center of your business, you can start to automate these processes. And we've seen this happen in other industries. If you take, for example, the automotive industry, you start to automate small portions of the process. So things like lane departure warning or parallel park assist. And after a while, you can start to combine these different automated subsystems to create fully automated processes. And that, we believe, will change the nature of work. It means that humans will not be replaced, they'll be assisted by these technologies, which will help them focus on delivering more value to their organizations. Now, the uncomfortable statistic behind this is that we believe from a manufacturing and production facilities perspective, it will put 47% of people will be displaced from their existing positions within their organizations. And we know that this will happen because we've seen it happen in other industries. We've seen it happen in the electronics industry with synthesis. And we've seen it happen most notably in the publishing industry with desktop publishing. If you think about the revolution that happened in the 90s with Apple and Microsoft and Adobe, where we transitioned from large centralized production facilities for print media towards desktop publishing, where everyone was empowered to create and manufacture printed media, you can see the implications that it had for that industry, the number of people that were displaced at that time. Now, the opportunity here is that those people, when they're displaced, have to go somewhere. They will create new businesses. And if you look at the media industry today, there are literally millions of new jobs that are being created thanks to the power of desktop publishing. And that's where we believe this concept of push-button manufacturing will play a significant role. And that is why we've developed Fusion 360. Fusion 360 is the platform for this push-button manufacturing revolution. What it does is it lowers the barrier of entry to anyone, and it creates a digital platform in the cloud that enables people to connect as part of a community. So we're also empowering people to connect from their existing desktop technologies today. So if you take a look at Fusion 360, it's sometimes difficult to know the difference between a photograph of the actual product and the technology that you're using to design that product. Because this is Fusion 360. At the heart of this experience lies a cloud data model that centralizes the information and allows anyone, anywhere in the world, to be able to connect to that information and collaborate as part of a single team, no matter what platform they're working on, no matter what part of the world that they're situated on. so that a distributed design team can act as a single unit and iterate faster and more effectively. It also provides all of the tools for free-form definition. So if you're doing styling, concept definition, all of those tools are included and combined with engineering tools so that you can maintain design intent throughout the entire process. It also includes cloud-based documentation. So you can take those designs, document them, and communicate instantly with anyone in your supply chain or supply network. And on top of that, it includes all of the simulation and analysis tools that you need to be able to verify design, to be able to look at its behavioral characteristics and optimize it. But more than that, it combines not just design, but the ability to be able to seamlessly, physically switch to manufacturing. So in this case, we can take this cast component and start to machine it, and we can do our 2.5 axis subtractive machining. But in this case, this design's actually been produced by somebody who's using Inventor. And using our AnyCAD technology, the person using Inventor, and it could be SolidWorks or Creo or any of the other tools, can update that design. They can drop it back into the cloud repository with Autodesk Drive. And inside of Fusion, all of the updates are consumed associatively. Not just the design updates, but it also means that the machining strategy is also seamlessly updated and kept in sync with the very latest version of the design, no matter where that design comes from. And it operates on any platform, whether it's Windows, Mac, or mobile. So the question people ask about Fusion, is it a CAD system? Is it a CAM tool? Is it a simulation application, data management? The answer, as you can see, to all those questions is no. It's not one of those things, it's all of those things. It's a complete product innovation platform that enables you to go from concept to physical production seamlessly. But just connecting that process isn't enough. As I said earlier, we need to empower customers with the ability to automate elements of this process. So let's take, for example, Lightning Motorcycles. Lightning Motorcycles make the world's fastest motorcycle. It's an electric drive motorcycle. It operates at over 220 miles per hour. So it's the fastest motorcycle on the planet. And in order to stay there, they need to be continually innovating. And that innovation is something that's driven by design engineering. And they're employing AGD, or Autodesk Generative Design Service. And they're using it alongside of Fusion. So here you can see a design for the Lightning Motorcycle with a conventional swing arm on the rear of the design. Now what we're going to do is basically isolate the mounting points and use the Autodesk Generative Design Service to be able to load up the assembly, tell that particular component what type of material it's made from, and then as you saw in the Airbus example, we use the power of the cloud to computationally generate not one, but hundreds and hundreds of different results spread across the potential solution universe. And we empower the design engineer with tools to enable them to explore that entire solution universe so that they can look for whatever set of trade-off requirements, whether it's the manufacturing process employed, the loading conditions, the material. They can evaluate 15 different iterations in this case to start to optimize that design for exactly the set of market requirements they've got in mind. And they can use Fusion's integrated simulation capabilities to look at the structural loading conditions. But just having produced the design isn't enough. They need to be able to switch across to the manufacturing environment. In this case, printing in metal sintering, so setting up the support structures in the build envelope. And then being able to take that information and simulate not only the design characteristics of the product, but its manufacturing characteristics thanks to our NetFab technology, which enables you to simulate the print build process and look for any shrinkage, warpage, or deviation from the nominal model. And with that information, you can empower our full 5-axis subtractive machining environment, which allows you to finish the product's manufacture in a completely integrated hybrid environment, all on one single platform, which is Fusion 360. That's why it's called Fusion. It takes all of these different elements of the process together and fuses them into one seamless environment that lets you realize innovative product concept designs and allows you, if you're Lightning Motorcycles, to continue to maintain that position as the world's fastest motorbike. But it doesn't just stop at the design and definition of the manufacturing process. You also need to be able to connect to, control, monitor, and maintain the manufacturing operation. This is another customer of ours, KMP Motorsport. They produce custom drivetrains for racing vehicles. And in this example, they use Fusion to do all of their design work, as you've just seen in the previous video from Lightning. But in this video, what we're looking at is KMP's ability to extend the use of data onto their shop floor with a new offering, Fusion Production. So this is an expansion of Fusion that takes the design information, in this case an upright from the suspension system, and it takes the CAM data, the manufacturing information that's being produced by the production engineer, and it extends the use of that information onto the shop floor so that we can automatically create setup instructions and methods of operations for the production engineers down in the shop. And the power of the cloud enables us to use mobile technology to connect to that information so we can scan the QR code of the incoming inventory as it enters our work cell and automatically gain access to all of the manufacturing instructions. We can actually look at the shop floor and reprioritize jobs, if necessary, in order to meet the commitments that we've made to our customers, because we can look at an individual machine tool and we can see what jobs are queued up for that machine tool. So we're able to track the inventory, we're also able to track the machine tool, and we can even provide feedback to the design and production engineers as to how that manufacturing process went and if we needed to adjust anything. On top of that, our IoT services enable us to connect to the machines themselves, so we can start to look at shop floor utilization of capital plant assets, which means that you as the manufacturer get a higher return on the investment that you've made in your capital plant equipment. So everything I've just shown you is part of the Fusion platform. It represents the future of making things. But of course, Autodesk has many, many customers that are using a variety of different tools and technologies, from AutoCAD right the way through to Inventor, our standard for design parametric engineering. And so it's important that we provide those customers, all of them, with a single, consistent path to the future of making things. And that single, consistent path to the future of making things represents our commitment as an organization to seamlessly combine and integrate design and manufacturing, which is why we've produced the product design and manufacturing collection, because we don't believe that you can separate those two disciplines any longer and remain competitively effective in the market. So let's take, for example, Radical Transport. Radical Transport make high-end hoverboards. These guys are hardcore Inventor users. They get absolutely phenomenal benefit out of working with Inventor as their premier parametric modeling system. They produce a stunning product. And as you can see, they leverage the complete power of Inventor itself. So all of the sophistication that we can offer in parametric design, plastic part fittings, all of the different robust parametric design capabilities that our customers have come to know and love over the last 15 years. Now, the one challenge I would put here is that if you're making an investment in parametric and 3D modeling and you're not leveraging that data in other areas of your business, you're not getting a true return on the investment you made. So take, for example, the operation of this product. As the user rides and corners, the loads move dynamically and transfer dynamically. You cannot use static FEA to solve that problem. You need Nastran, nonlinear simulation. So we've included it in the product design and manufacturing collection. It runs directly inside of the Inventor window, as does all of the 5-axis subtractive machining that you see happening here as well. So inside of one single subscription, you get access to all of our cloud-based Fusion technology that I showed you earlier, as well as seamlessly integrated nonlinear simulation capabilities with Nastran and 5-axis subtractive machining capabilities that run directly inside of the Inventor window and are managed seamlessly by Volt. So now you have a path between where you are today and the cloud, which allows you to embrace that new future technology at a pace that suits you. So what we've done, as you can see, is we've built a single platform. It places your data at the center of what you do, and it provides you with tools to enable you to connect the entire design process right the way through from conceptual design to nonlinear simulation, takes that design through on into manufacturing and integrates it so you can optimize for manufacturing. You can connect to the manufacturing process itself and your product, and so you can design, optimize, monitor, and iterate on the production process all in one single platform. It's complete, it's connected, and it's instant on. Now that platform starts with Fusion at just $25 a month. It's even free to startups, to hobbyists, and enthusiasts. So I hope you can see it literally empowers anyone, anywhere, to make anything. So thank you for your time. I'll hand you across to the next speaker.